So we'll go on to our lightning talks. We have 4 of them. Since we have 4 lightning talks in 15 minutes, I won't be strictly enforcing the 1-minute time limit. And I see there's a comment from Jamie that of a TOI that does have a astroseismology mass and radius for the star. Okay, cool. Thank you for that, Jamie. Yeah, so we'll have time to take a question or two after each lightning slide as well. So let me share my screen. Let's get started. First lightning slide from Jia-Yi.
Hello, everyone. I'm Jia-Yi from Nanjing University. I'm talking about the occurrence and architecture of Kepler planet system as function of stellar mass and effective temperature. We combine the Kepler DR25 planet catalog and with Gaia DR2 revised stellar radii, we calculate a planet occurrence rate with different stellar effective temperature. We found that first, as the left panel shows, the fraction of stars which have planets drops about 35% to 30% from about 3,000 K to 7,000 K. And the average number of planets per system also drops about 2.8 per system to 1.8 per system. So both of them decrease as temperature increase. Thank you.
And do we have any 1 or 2 questions? Is this affected by the size of planets that you're sensitive to around these different temperature stars?
Sorry, could you say it again?
Yeah. Does the fact that maybe you can only detect the bigger planets around the hotter stars play in here, do you think?
Yeah, we consider the detection efficiency for different stars, and we correct this problem. So we think this is the real occurrence rate, not affected by the planet radii.
We have a question about if there's any dependence on metallicity. I don't know if you have metallicity for these stars.
We compare the metallicity for different beams, and we do the KS test. And the KS test shows the stars in different beams do not show significant metallicity difference.
Well, thank you very much. We'll move on to, yeah, we have a couple more questions, but maybe you can respond to those in the chat box.
Okay.
All right. So I'm going to talk about how ultra-short period planets commonly have neighbors. I've been working on this reanalysis of K2 systems for the first 10 campaigns, and towards the end, I was like, somebody needs to go through and systematically look for companions to all these planets, because there were 11 or 12 systems that had planets. And so when I did that, I found I doubled the number of systems with new planets. An example is the system off on the left, where the ultra-short period planet is actually this really shallow thing. And then somebody else found a planet out about 4 days. And then when we look through, there's a very clear planet at 27 days. We have three transits of this planet. Ignore the bottom panel. I was just looking to see if there was a 4th thing in there. And so when we did this for all of our systems, which are plotted in the middle, these are systems where they're all to scale, so the size of the star and the separations of the planet, and even the planets themselves are plotted to scale, though you can't see it on here. We found that we've got 23 systems with multiple planets. Some of them are confirmed, some of them are not quite confirmed yet. And that's a very large fraction of ultra-short period planets to have close transiting companions. These are all within about 40 solar radii away. So these are short period companions. And then the other thing I was looking at is noticing, that these M-dwarf systems tend to be a lot more compact, which could be a little bit of a transit detection bias effect, because you're more likely to detect a transit over a bigger star, all else being equal. But when you plot the ratio of the separations, we find that there's actually a pretty clear threshold that the ultra-short period planet is separated from its next closest planet. This is the red line on the plot at the left, by about a factor of 2.5, which means that these things, the ultra-short period planets, are not super close to the next planet in most of their systems. And so the fascinating question is, how did these systems get quite so close to their planets? They had to have come from somewhere else, we think. They couldn't have formed at periods of less than a day. They came in groups with a bunch of other planets, up to 4. There's a bunch of cases of 3 and 4 planet systems, and these are just the transits that we know about. And they're all fairly nicely aligned because we can detect transits of multiple planets. So I think there's a lot more work that needs to be done. I think every single one of these systems needs to have somebody go monitor it long-term for RV planets to see if there's more stuff even further out, like in the Kepler 88 system. And it seems that, a third of ultra-short period planets are known to have companions. I bet a bunch more do that we just haven't detected. So that's what I've been working on.
Have time for a question or two? With that example you showed on the left, why do you think that 27-day planet was originally missed? Is it an issue of once you remove the transiting planet, it cleans up?
Yeah. So for a lot of these ones that were missed, there's 2 reasons. Before, I had noticed that there tended to be a pattern where the ultra-short period planet was smaller than the outer companions. And that's a little bit of a detection effect. If you're stacking up multiple planets, multiple transits, it's easier to see smaller planets if you can stack 20 transits as opposed to 5 or 10, all else being equal. And then there's also some cases where if you've got 3 planets in a system and they're all relatively faint, like you really need to systematically subtract out each of the known planets to find the outer ones, because some of these systems were just a little messy with all of the planets in there together. And the second reason is because, honestly, it takes extra work to go look for the next 2nd, 3rd, 4th planet in a system, and most people just haven't done that for all, thousands and thousands of K2 and Kepler and TOI systems. So, and the longer answer is, I don't know why that one was missed. That one's a pretty clear planet.
Yeah. Okay. Thank you. Have a couple. Let's do one more question, then maybe you can address the others in the chat box.
Yeah.
Jake Clark asks, "What do you know what the rough V magnitudes are for radial velocity follow-up?"
All over the map. There are ones that are 11th magnitude. There are ones that are 18th magnitude. So some of these are definitely follow-upable.
Great. We're going to move on, but Elisabeth will address some of these other questions in the chat box. Let's go on to Bernardo Pereira.
Can you hear me?
Yes.
Thank you. So thank you. My name is Bernardo, and I'm a graduate student at the Universidade Federal de Minas Gerais. My current work is searching for solar-like oscillations in exoplanet host stars observed by TESS, and determining their stellar parameters using global asteroseismic properties. In this talk, I'll show how we're extracting those properties, in particular from more evolved stars whose oscillations occur at lower frequencies. On the far left, I show our results for a star previously analyzed by Campante et al., and you see that we've obtained consistent values for delta nu in lumens. Our first method is shown on the second column. We take multiple spectra of the spectrum using a moving window of increasing width. Those windows can be seen on the inset graphic. On the outside, we see the results matched by the colors, where we can see a clear peak around 8 microhertz that corresponds to delta nu over 2. Our second method is shown on the right side, and after passing a filter of evenly spaced delta functions on the spectrum, we calculate the integral. We repeat this process varying the filter center and spacing, as is shown on this grayscale figure. Local maxima appear every time the filter matches the oscillation peaks. And as you can see on the rightmost figure, this occurs for a filter spacing around 8 microhertz again, which corresponds to delta nu over 2. We can also estimate mu max by averaging the filter center at the maximum. With these values, we can proceed to accurately determine stellar parameters using, for example, grid-based modeling. Thank you very much.
Great, we have time for a question or two. How many targets do you expect will be amenable to this?
So I've searched visually pretty much every star that TESS has observed and has an exoplanet confirmed. And I found 30 or so specters, but we are hoping to work with 10 for my project.
Great. Any other questions? Oh, how does your, Jamie Taylor asks, how does your pipeline deal with spurious peaks in the power spectrum?
Can you repeat it, please?
How does your pipeline deal with spurious peaks in the power spectrum?
I'm not sure I know the word spurious.
Oh, like fake or extra or stuff that you don't want to deal with in the power spectra.
We're pretty much counting on the visual inspection of the oscillations first, and using multiple methods and making sure that they give the same results, consistent results, using independent ways of obtaining the parameters.
Great. Let's move on to our final slide from Eric Agol.
Great, thanks. We've gathered more than 400 transit time measurements of the 7 planets in the TRAPPIST-1 system with Spitzer K2 ground-based telescopes, and over a time span of more than 3 years. The 30-plus co-authors on this paper actually include Exostar participants Adam Bergesser and Dan Fortner-Mackey, and some of the code development was done while I was at KITP. This work has been submitted to the Planetary Science Journal. So from these transit times, we can derive the mass ratios of the planets to the star from transit timing variations. From the light curves, we actually re-derived a photodynamical model, which is what Lauren described, to get the radius ratios of the planets to the star, as well as the density of the star. And then a luminosity measurement for the star yields a mass for the star based on the Mann-et-al relation, which actually co-authors include Exostar participants Eric Gaidos and Greg Fudden. So from those data, then, we can derive the radii and masses of the planets. So the plot shows planet radius versus planet mass in Earth units, the posterior distributions with 1 and 2 sigma uncertainty ranges. And the coloring is given by equilibrium temperature, which is basically a function of the installation of these planets. So what you can see from this plot, the dash curve shows a fully differentiated model with the refractory abundances given at the bottom, which goes through the Earth and nearly through Venus. So this would be an Earth-like composition. You can see that all the posteriors are lower density or larger radius than this composition, so they're inconsistent with an Earth-like composition. The magenta curve shows an Earth-like composition, but without a core. So all the iron has been removed from the core and oxidized and placed in the mantle. This addition of oxygen creates a lower uncompressed density, as Diana described, and therefore a lower density for these planets when compressed as well. And so you can see that this model is consistent with the 1 sigma posteriors of all 7 planets, which is fascinating. This is not a unique solution. They could have lower iron abundances. They could have more enhanced water abundances. Now we derive in the lower left table, you can see the precisions for the radii, masses, and densities of the planets. The radii are 1 to 2% precision, the mass is 3 to 5%, the density is 3 to 8%. Several of these are limited by the stellar precision, so we need to improve the stellar precision to get better planet masses and radii. The inset panel in the figure shows the mass, radius, luminosity, effective temperature of the star, which is 26 Kelvin uncertainty, Pierre, if you're interested. And so from the masses and radii can constrain the compositions, which we've done with preliminary exploration of this paper. It'd be great to try out Diana's methods on these. So there's scheduled 4 JWST guaranteed time observations of TRAPPIST-1. There's a community effort to coordinate further transit observations of the system. So we should improve both the transit timing, transit depth, and their stellar density measurements, and therefore improve properties of these planets with JWST. Great, thanks.
Thank you. We have a question from Carrie Lice, who said, do we know if the TRAPPIST-1 primary is deficient in iron versus solar?
It's consistent with solar. And we don't know, there's another question, it looks like, about the iron to magnesium and magnesium to silicon values for the star. We don't know if solar applies for the star, but those haven't been measured to my knowledge.
And one more question from Lauren Weiss. How did the densities compare to the minimum rocky density Diana presented?
Yeah, I don't plot that here, but it's above that magenta curve. It's actually above all the contours, so these are not consistent with a pure rocky composition. If you take a fully differentiated model, they're all consistent with about a 17% by mass iron fraction. Diana mentioned that the Earth is about 33%, so that's about half of the iron abundance of the Earth if these were differentiated. And that's well in the range of the range of iron abundances, iron to magnesium and iron to silicon abundance ranges of other stars. Again, that has not, those ratios have not yet been measured for TRAPPIST-1.
Well, let's thank virtually all our speakers, both our main panelists and our lightning talk speakers. We're now going to have approximately a 30-minute break, and then we'll come back for our final session. Thanks, everyone.